Prescribe data G on the complement, and I call those data exterior data. Yeah, let's not call it Poisson equation because I want to prescribe some non-local data here. I will define this non-local derivative on the complement, and we will study these two problems. Also, I intend to speak about non-local to local limits. There's various ways to consider non-local to local limits. One will be to send S to 1, where these problems then become the classical problems for the classical fraction, for the classical P-Laplacian and the classical Laplace operator. And then last, I intend to tell you some new information about the parabolic Harnack inequality for non-local problems. Now, there's something that I would like to point out. I have formulated here these problems for translation invariant operators, for, so to say, simple model examples, but all I'm telling you applies with only simple changes, basically no change, to more general operators. So, let's formulate it as follows. The approach applies to non-translation invariant operators. So, in all I'm saying, you are welcome to replace the fractional Laplacian by operators of this form, where K is merely bounded. Oh no, that's not what I want to say. Measurable. So in particular, not continuous. Okay. So these are the aims of the 4 lectures. Let me give you 2 wrong assertions in this field that have been clarified, but they tell you where possible problems arise, what might be interesting. So let me give you 2 wrong statements, which I find instructive. Take a bounded open set D, take an L1 log function, assume that it is subharmonic in the sense of distributions. That means tested against smooth functional compact support. And assume U is less or equal to 0 in the complement, then so this is wrong. Why is that wrong? this is wrong because you don't prescribe anything at the boundary. So saying U subharmonic in D prime, you know what that means, right? It means that U phi less than equal to 0 for all phi.
One cannot see.
Say it again?
One cannot see the chalk.
Oh, the color is bad, that's what you say, right.
Other color.
Yes. So I guess green will be bad too. Yellow might be good. So star just means that okay, this is wrong because you don't prescribe anything about U on the boundary, and there's various ways to fix it by adding additional assumptions. But you will see today a function space which would solve the problem if you assume U to be in this function space. But optimal assumptions is actually complicated to give a result which has not so restrictive assumptions on U. And you might want to check a paper that addresses this. It's about by two of the guys listed there. Florian Gruber and Torben Hensi. You find it on archive, and it says something with maximum principle of something. Let me give you the second wrong statement, and I guess I should put it here. The second wrong statement is the following. Assume U is a function depending on time and space, is non-negative, let's say on 0, 2, V2, 0. And DTU then UTX less or equal CU as Y for T less or equal S, let's say less or equal 1 positive, and X and Y in B1 with C independent of U. So that would be a certain type of parabolic harmonic inequality, but the assertion as it's written here is also wrong and is not so simple to fix it. And there's up to now work on this direction. For the experts, let me highlight here, I didn't put any distance between T and S, but here the main problem is that we don't assume anything on U outside the cylinder where we have the equation. So tails will be extremely important. Tails can destroy a lot of results. And if you want to look into a possible way how to fix this wrong statement, so I shall put the guy because it's a wrong statement. And if you're interested in finding or in reading what one can do, you might want to go to a recent article by myself together with Marvin Weidner, who's currently in Barcelona. All right. So tails and boundary behavior are very important. And in particular, they are important for non-local operators. And sometimes, in particular, the boundary behavior, things are similar to what you know for local equations. But even for boundary behavior, things might be different because the exterior data live in complement. But for tails, of course, this is something which you don't know from local operators. So let me add one more section to the introduction, which is known to many of you, I'm sure, but I think it is very important for people, for PhD students in the area. So I want to quickly speak about divergence versus non-divergence form. And this will be very fast. So a classical second order differential operator in divergence form can be written in this way, where a classical operator in non-divergence form can be written in this way, right? And I think the vast majority of people working in analysis agree that one of the two forms is much more important than the other, and they disagree on which it is. So here you work with a variational or energy approach. You cannot evaluate this operator pointwise, even if you will see infinity. So you need like the energy approach and to work with test functions, whereas here you have a pointwise or classical solution, and the viscosity solutions form a natural framework for this. Now let me quickly tell you that when studying non-local operators, you have a similar but not totally equal splitting between the non-local operators. And let me try to explain it in the following way. So let me fix coefficients k, x, y and mxy minus x, which are non-negative. So I have a function kxy, and here you can write it mxh, but h is y minus x. Then let's assume for simplicity that, yeah, maybe, yeah, okay, we shall not, this line somehow, because I will now write something which contradicts this line, but so we have two different cases, so then the line is still okay. Okay, they will not hold at the same time, then it's okay. So let's assume symmetry. Then a non-local operator where you work with a variational approach is maybe given in this way. Where when you have the function m and you assume a different symmetry, then let's call this operator LU at x. And here we define on the other side AU of x And then in front of you are two operators which have a lot in common with these operators. Even they appear as limiting operators if you consider the correct sequences. You cannot evaluate this operator pointwise, even if you see infinity, because k might not allow that. So this is the left-hand side, this is the right-hand side. And now what I want to tell you is that the two sides, they coincide when you have constant coefficients, exactly the same way it happens here. If this matrix A, where the entries A, I, J is independent of X, of course, you can just bring it in or out. So maybe we want to have no minus sign here, so it fits to those guys. So here the observation, so to say, we can maybe the observation is constant coefficients so this somehow now finished here, this splitting. Constant coefficients mean we have translation invariant operators. Which means in this setting that kxy is equal to some function depending only on the difference. And it would mean that mxh in fact is independent of x. And it then means if we put a half here, so that would have been good to put a half here, it then means that L is equal to A. So for those of you who have seen this many times, I apologize, but actually I remember when I was a PhD student, it took me quite a while to see that these are two different kinds of symmetries, this one and that one. This can be seen as a divergence form type non-local operator with symmetric coefficients. This can be seen as a non-divergence form type non-local operator with symmetric coefficients. And if you are in the translation invariant case, they coincide, so you get exactly the picture that you have. So this was the introduction, and now we should directly begin with the first math chapter.
So your constant coefficient is AIJ is constant.
Yes. So this thing is very convenient, this border one, but it's rather small. Okay, chapter 2. So, what is the starting point? Let's choose a starting point that many of you, I'm sure, know. Assume U satisfies this equation in a bounded open set, and U is 0 on P complement. Assume U is rather regular, so assume it is given. So so to say, this is 1. Yeah? And of course, 1 means, if we spell out what this thing is, it means that now we multiply.
So D is a bounded domain.
D is at the time is a bounded open set, and I use D as a domain. Yes. If we multiply this equation on, let's see, both sides with U and integrate over RD, then what? Then we obtain the double integral RD, but U is 0 on the complement. That means D complement does not appear. So one option to write it, and I agree that this is really weird, you write this. So this is the product RD, where you remove D complement. And you can remove it because anyway you use 0 there. So you get this. And you get this, right? Now what I can do, I can write a minus here and 0. Yeah? So you see that this is 0. And what does that mean? That means if we call this whole thing I of U, we can realize solutions to problem 1 as minimizers of such a function. Yeah? And this is, in this context, a simple starting point. So weak solutions to this problem will appear as minimizers of such a functional in the space where the energy is finite and functions are 0 on the complement. So that's the first message. We will look at subspaces of L2 with finite energy, and in particular, those subspaces where U is 0 on the complement. They are useful to study those problems, to set up weak solutions. So
why is that equal to 0?
You ask about this equality? Okay, so we have left equal to right, which means left minus right equal to 0. So I've changed the equality to a minus. Okay, now.
Excuse me, ma'am.
Sure.
I also have a related question, perhaps silly. We are multiplying the equation by U of x.
Yes.
And right there we get U of y minus U of x squared.
So
is there any multiplicative cost?
No, so what you want to do, you want to maybe perform this once for yourself. You take this guy, multiply with U of x and integrate. And then you just split this in half the guy plus half the guy. You change x and y and you see this quadratic term appearing. So that's something one has to do a couple of times before you somehow find it natural. So let me make an important remark. Finiteness of the energy implies finiteness of so automatically U is in a weighted L2 space. This needs a little argument. You might want to work this out, but it's not complicated. But this information comes out secondary. And you will see for general Levy measures, which we will now introduce, this is not so trivial. So you don't really know, or you have a lot of freedom where to set up, in which L2 space you have to want to set up your problem. So let me make the point once again. So you begin with, if you want a Levy measure or some measure, here it is. Here you see it already. And you generate a measure on L2, which creates a good L2 space. Yeah. So here it happens automatically, but you might, in the general case, you might have to work a little bit. So I mentioned Levy measures, so we should now introduce them. So definition 1. Definition 1. A measure new. A radon measure on the Borel sets of RD, where we remove 0, is called Levy measure. If the following expression is finite. Very often we will consider Levy measures with a density. For more experienced participants, let me say that when you have Levy measures without a density, the difference between divergence form and non-divergence form becomes a huge issue, because in the divergence form, the energy world, you have 2 integrals, and you can treat very well jumping measures without density. Whereas for non-divergence form, it's a huge problem. Until now, there's no Alexandrov-Bakelman-Pucci maximum principle for singular cases. There are candidates, ideas, and so on. So when you do not have densities, somehow then really the double integrals help you a lot. They make things much easier, and you can prove wonderful, remarkable results. But this is just due to an extra structure. I guess that we will most often only look at Levy measures with the density. So this brings me to my first interlude. So of course, this is a course, so this is for you, and I asked you for feedback in order to make it, the series of lectures even better. But of course, I want to benefit too. Yeah? I mean, first I benefit because I have fun, that's true. But also I have some open problems. And here's one. It's an exercise, and I think it's rather interesting. So how to formulate it? So let mu be any radon measure. So just borrow a regular measure on so under which conditions is the following assumption true? Does one need any additional assumption, and if so, which? So for the oder 4. Now comes a statement to be true. And the statement is the following. Mu is a Levy measure if and only if this is finite for all smooth functions with convex support. So I don't know the answer, but I know partial answers. Of course, if mu is Levy, then this quantity is finite. This is just Taylor, you will see. So this direction is simple. My question is about this direction. Yeah? So here we can put a check mark. But this direction, I can put a check mark in parentheses because I know it. If it's a radial measure, I know it. I know how to prove it. But I have many examples of non-radial measures where it's true. Somehow I get the feeling it might be true every time, and then I would like to put it in the book that I intend to write because it's such a beautiful result. If it's true. So I don't know. Okay. So now function spaces. Azara, can you give me a 5-minute to the end warning? Not now. No, 5 minutes to the end.
Up to the end,
Yes, thank you.
Absolutely.
Okay, function spaces. Definition 2. So our setup is let nu be a Levy measure with a symmetric density. So a symmetric Levy measure with a density. Let D be a bounded open set. I forgot. I will add it to this remark. I want to add something which I learned which was pointed out to me many years ago by Shavib, and I like that. And I want to mention. I will do it later. Okay, so then first definition: the space V nu D RD. So D RD is the space of all functions u from Rd to R, measurable with finite semi-norm. So where I will define the semi-norm in a way which by now should not be surprising. It is just dx. And we endow this space with a norm. So there's a norm on this space, and the norm is, there's many norms, of course. So one option is to put the L2 norm of D plus this. So this gives us a norm. Now, we also define the energy, but it's the one that you have seen before. Yeah, it's basically floating around everywhere. We define, this is still part of this definition 1, EUU as this strange product Now, definition is finished. Let me comment on it. So definition stops here. A little remark. So wait, 1, 2, 3. I wanted to put. So this is actually just one definition. Okay. And the remark, that's the obvious remark, is that the semi-norm is comparable to the energy in a trivial way. So here you have the integral d rd and the integral rd d, and in the semi-norm you just have it once, but by symmetry you just count plus. So
in this definition, do you need U to be vanishing outside the domain B?
no, and I don't want that. Not at all.
Arbitrary outside B.
Absolutely. Yeah. So you say arbitrary, but the finiteness of this semi-norm implies immediately a decay of U at infinity. The finiteness of this double integral has a meaning for what U does at infinity. What is the optimal weight is actually a tricky question, yeah? Because these Levy measures, they can be very, very weird. Even when they are radial, due to oscillations, they can create weird behavior at infinity, and you can get a lot of things wrong. So
could I ask a relevant question?
Sure.
That in your definition of Laplace to the S power, do you need U vanishing outside D or just?
Not at all. No, I would be very sad if you vanished outside, because for me it's important that I would have no exterior data problems anymore. No inhomogeneous exterior data. No. If I speak about a non-local equation in a bounded set, it means the equation holds true for every point in that set, but it implies in most of the cases that U is a function defined everywhere, and it doesn't say anything what happens outside of D. That needs to come into function spaces, or for well-posedness you might have assumptions and so on. But a non-local equation being true in a bounded open set does not tell us, it might be implicit, but we don't prescribe to start with what U is doing outside the domain. So here I said, let me add a comment here. So usually weak solutions, the variational approach is much weaker than the classical approach. So a classical solution is a weak solution, and a weak solution is only a classical solution if you have smoothness, which you might be able to prove. But with these tails, there's something, and many, many years ago, I learned it from Xavi. So the variational approach immediately has this weight in L2. But if you want to study this equation, if you want this object in a classical sense to be finite, this requires you only to be in a weighted L1 space. You can adjust your variational approach, but I will never do this. But it's possible to play with this. But note, so this comment should have come here. Note, so to say, well-posedness of minus Laplace u at x at some x requires smoothness around x. Okay, that's one thing. Let's say regularity of u at x plus u, and now you see L1 of RD. Oh, sorry. And this is weaker than here. So somewhere in this sense, there's a little twist for these variational solutions or approaches that if you work in those L2 spaces, somehow you lose some generality. You can work this in, yeah, but we will not do this. Okay, now we need some results, right? So we need, first of all, we need to understand. So you asked the question how I look at this V space, whether I can describe anything outside. Ah, we were here. So I would like you to think about this space as a non-local substitute of H1. Yeah, so this is not a theorem or observation or anything, but I would like you to think about this space as a non-local substitute of H1. And we will now introduce non-local substitutes of H1 not and so on. Okay. Definition 3. No. Yeah, maybe, right? 3. Thank you. That will be fast now. Under the same assumptions, we define the space with a little 0 here as the space where we are 0 on the complement, and we define the corresponding, you might want to say Sobolev space, as this is finite, where the energy with a subindex d is just the double integral over dd of the quantity that you will expect. So no surprises here. Now, let me give you the first result. Before doing this, let me say that in the same way, I can write it. No, it's better here. I would like you to think about this space as the non-local analog of H1 not D. So we need density results. So I summarize known results about density in these function spaces. Let's make one additional assumption. Let's assume that nu has full support. So let nu be a symmetric Levy measure whose density has full support, or the measure has full support, what we have said, but I want the density too. Let D be open. Let's be open. Do I need, I think for this I even don't need boundedness. So I think, let's check. I claim I need only boundedness. So then one can prove the following results. Now, what do you want? Now, we want the results that we know for Sobolev spaces because we know what they're good for, right? You need density in all, not in all, but in many areas. And as a probabilist, the density will give you regularity of the Dirichlet form, which gives you the existence of a stochastic process. And we will not have time to speak about reflecting processes. There's really very recent interesting things going on for non-local operators, and density turns out to be a very crucial ingredient. So, Myers-Serrin for non-local spaces is, for instance, this result. This is dense in H nu. This is a Myers-Serrin type result. Now, if, let's make the assumption, assume that the boundary of D is compact and continuous. Then you can show that if you go up to the boundary, this is dense. In H nu. But of course, we are interested in the V spaces. Same assumptions. So assume the boundary is compact and continuous. Then we can show that the smooth function with compact support is dense in V nu 0 RD. And very important is the last result. You want to remove the 0 here, right? You want to be smooth in V nu. And this we can prove under the assumption that the boundary is compact and Lipschitz. Then we can show that smooth function with compact support in RD is dense in V nu DRD. Now, you have seen a norm already, and of course, if I don't claim anything otherwise, then it stands with respect to that norm, but you can also prove density with respect to a second norm. It stands, so let's say, let me continue the sentence saying with respect to, of course, the norm that we have seen. And with respect to another norm, which I define by putting 3 bars. And this is just the L2 norm of RD, so it's a very strong norm, plus the same norm. All right, good. So now we have achieved already a lot, and I guess I have maximum 20 minutes left or so for my understanding or feeling. But now maybe we should make some little computation together, yeah, so to understand the space a little bit better. And then I want to introduce something like the Gauss-Green formula, because we also want to treat inhomogeneous exterior data. So far you have a lot of tools at hand for data 0 outside of D, but of course we want to treat data non-zero on the complement, and that's why we need to look at Gauss-Green formulas. Let me mention that this density result, if you want a source, so this is proved in different papers by different people, I guess 2 or 3 results with my contributions, but you find everything explained nicely, including some little mistakes in the literature. In a paper by Guy Fogem and myself, you find it on the archive. Let me mention something. There's the dissertation thesis of Guy Fogem is a beautiful source for the Hilbert space approach to non-local operators. So you might want to check out the full name of the guy is Guy Fabrice Fogem Gounoué. And you might want to check his PhD thesis, which is available on the web. And it has many beautiful computations. Also for the constant in the fractional Laplacian, he has a unique way to compute the constants there. And I guess there are some hidden gems which you don't find in other sources. Okay. Okay, now we have seen the D space, and let's play with this a little bit. So now there was a lot of theory and definitions and so on, but somehow we should maybe take it slow. So notation. We will see this tomorrow. If nu of dH is just h2 minus d minus 2s dh, yeah, what it is for the fractional Laplacian, then rather than writing v nu dr2, we will write vs d. And then later, this will come tomorrow, you will also see VS2 or even VSP for the fractional P Laplacian. Yeah? So this is equal to VS2. So it's good to introduce it today so that you can get used to this notation. Now computation. Let's try to understand the space. Example. Let's choose the unit ball in RD, and now we want to understand how U may look like so that it is in the space. Let's use this for the fractional Laplacian, right? Because we work with this guy anyways. So, of course, the regularity inside we understand. So being in this space is like Sobolev regularity inside, which we understand. Very far from the domain some tail, we understand. But what happens at the boundary? So what is going on across the boundary? So which regularity does the V space encode? Yeah? And for instance, I don't have time to formulate it. If you want to spend time the next days for symmetric Levy measures to prove Hardy inequalities, that is, you are in a V space and you prove some Hardy type inequality. I mean, many in the room would be very interested to see. Some results are known, but the general theory does not exist. So let's use an example. U of x. Let's do the following. Let's put it to 0 for x in V1. Let's now do something x minus 1 to the power beta for x in B2 minus B1, and then 0 for x in B2 complement. So beta is a real number. So how does that function look like? So this is the rotation symmetric function. So I should be able to draw the profile, right? The function is 0 here, and it's 0 here. Okay, good. We understand that. And now, when beta is positive, it increases. So here's the level 1. I think we could fix that. Change this distance. Oh, yeah, it's not so bad. So it could increase like this. That's an option. But if beta is negative, it could also come down from here. So this is beta negative, and this is beta positive. So my question is, given S in 0, 1, find conditions on beta such that, or which are equivalent to u, this function u, being in V S V1 RV. And this is just a little computation by polar coordinates, and I let you do this until tomorrow, and I tell you the answer tomorrow. So it's fun. So what you do is, I mean, so how you start? You just write. But basically now I'm doing it, right? It's not good. So you write it. Now you plug in u, maybe u is 0 in many areas in this double integral, and then there's some interchange, and then there's some integral where something at the boundary happens, and then blah blah blah, you do it, and then you find this is finite if and only if beta is greater, equal, less, or equal, I will not tell you, okay? So this is so to say the solution to the exercise. And tomorrow I'll fill in the gaps. Okay. Now I would be very happy if we could finish today's lecture also by me introducing the normal derivatives, because it fits perfectly. Or I do have a watch actually here on this.
So you have a clock.
There's a clock on the wall.
Perfect. 10 minutes is okay? No, I do have 90. Oh, I started 9:30. I have 25. Perfect. Oh, sorry. I thought like Gerald, you started quarter past. You started 9:30. Cool. Okay. I'm not doing it anyways. But it's really nice and fun. Okay, then I can take it. Okay, so. Now, in a certain sense, we have the setup. We have a Sobolev type space where 0 is prescribed on the complement. We have the corresponding energy space where it's not nothing is prescribed on the complement, and they are really these analogies are very, very good, because if you have H1 of D, it's not like that anything can happen on the boundary. It's not true, right? You know trace theorems. You know that functions in H1 have a certain property at the boundary. And the same thing is true for these V spaces. If you are in the V space, it's not true that anything can happen on the complement. If you are away from the boundary, yes, then it's just integrability and you can do weird things. But across the boundary, being in a V space has very much similar effect than being in H1 has effect on what happens close to the boundary, which is often described by the Hardy inequality. And as I said, Hardy inequalities for these general measures, Levy measures in V spaces, is an interesting subject. Okay. Okay, let's do the following. So we are in chapter 1, and I want to define a non-local normal type derivative. Let's do as follows. So definition 5. I think we had theorem 4 after definition 3, so that should be definition 5. So let P be open and mu be as above. So mu then for y in RD minus the closure of D, we define I like Y minus Z more. DZ. Which we call a non-local normal derivative. Now, remark, if our domain D is here and Y is here, what are we doing? We integrate this difference with respect to this measure, so it looks like just the operator, like the fractional Laplacian, so there's almost no difference, but note the integral is only with respect to D. So the points Z that matter or that are taken into account are only in D. So,
Excuse me, in this definition,
yes.
do you require this total measure of mu is equal to 1 or the integration equal to 0?
I didn't understand. No, can you please repeat your question?
I'm sorry, I'm curious why you're putting uy there in the definition. Is that because the integration of mu is equal to 1 or?
No, no. You will see now a theorem which tells you exactly why this form is the most natural. So give me a second for this. Let me first give you some physical interpretation if you want. So you look at those differences and you put the Levy measure as a weight, the Levy measure of this vector, so to say. Yeah, this of course looks a little bit like something if y goes to the boundary, that could be somehow, if everything would localize, that somehow could be an approximation of some non-local, of some normal derivative here, right? That's not excluded, right? If you take a normal vector field and you think about finite difference approximations, I mean, you would create something like this, right? Here we integrate over all these differences, so we take into account a lot of z's from D, okay, and y might be far, but somehow I think this analogy makes pretty. Note, there's no issue of principal value integral here because the singularity is gone. So note, y minus z is always positive. It's a trivial comment for z in D. And y. So let's say no PV needed here. Okay, now the striking result is lemma 6. I'm playing a lot with these analogies between classical Sobolev or Bezov spaces and these V spaces. What is a very known and important fact? If, for Sobolev spaces, if you minimize gradient V squared over D in H1 of D, then automatically the normal derivative of V is 0. If we minimize, then, oh, this nu is not a Levy measure, or we should not. So let's do the vector in essence. So this is very standard. That is not a big result. You just minimize, so you know the solution is harmonic. So you can then use, at first you use test function with compact support, you get harmonicity, then you start over, you use test functions in H1, you use Gauss-Green, and you get. The same is true for non-local operators. So, and that's of course beautiful and tells us that this definition is makes very much sense. So, let F be in L2 of D. Assume U in V nu D minimizes the functional, and we have seen the functional at the beginning of the lecture. It was called I. Now it is this is the energy with a half factor here. So I could have just said energy. V, okay. If U minimizes this functional in the space then automatically NU is 0 in the complement. That's why you might want to call it a natural derivative in that space. And this analogy, of course, to this thing is striking. Okay, so I want to then finally introduce Gauss-Green and tell you something about Gauss-Green. An option would be just to introduce the VSP spaces and go to the fractional P Laplacian, but I think we better do this tomorrow, and then it's nice that we have some repetition of the spaces. I think that's very good. Okay, now last 13 minutes, some comments about Gauss-Green. I'm actually surprised that I managed to cover all the material. I miscalculated. I thought I would run short of time. It is good for tomorrow. I think we can do a little bit more. So we had lemma 6, and then we have proposition 7. For U in C2B, that means bounded in RD, and V in C1B, we have the following formula. So we have not seen the operator L already, but I think you know what it is, and I will explain it in a moment. So the energy should have, this should have a half now, which is already a problem. So this is just a Levy generator. So, after lemma 6, I guess it's not so surprising that even something like Gauss-Green holds true. In fact, you need Gauss-Green in the proof of lemma 6. So yes, exactly. But I really would like to think you an analogy. So think about this being the Laplacian. Then you get gradient u squared here, the energy, and then you get minus the normal derivative on the boundary, yeah? And you get all the same. Now, in order this to be fine, to exist, you need some regularity, and that's why, I mean, this is of course not optimal, but this is just here in order this to exist. Yeah? So nothing is optimized here. Most important comment, this is the translation invariant case, and the same Gauss-Green type formula holds for coefficients k, x, y, because the proof of this thing is just Fubini. So please, I mean, that's really an exercise I want you to do as much as I want to do the other exercise. So the proof is almost nothing. You just interchange integrals. So the intellectual achievement is here to give names and symbols to the objects. So that this is not a deep result. It's just somehow very nice that we can put names and group the things in a way such that we have an analogy to what we know. But what is maybe interesting for some of you,
Excuse me, can you remind us of the CB definition?
yes, so this means continuously differentiable, and this means bounded. And if I put it here, and then I also assume that the derivatives are also bounded. Yeah. But somehow, as I said, this is not optimized by no means. So let me say something interesting. So proposition, bless you, can be used in order to prove the classical divergence theorem. I mean, it's not really proposition 7, it's ideas, so to say. Let's say proposition, let's say ideas.
Excuse me, the energy is not E, U, U, E.
Excuse me?
In that part is not E.
Oh, yes, it is. Thank you very much. Of course. Thank you. Ideas like proposition 7 can be used to prove the classical divergence theorem in bounded C1 domains. So you might want to check the paper by Solveig and myself in archive. It is not a publication with a deep new result, but somehow we got a lot of traffic, if you want, because people seem to like the idea. So what's the idea? The idea is such a formula is just an application of Fubini. You can use sequences of kernels that approximate, such that all these quantities approximate the corresponding local properties. So, if you allow me to raise this here, what is possible? It is possible to choose sequences of measures, nu epsilon, and
Sorry, you have 5 minutes.
Thank you. I expect that. The newest inside, so it's in fact L epsilon. I was searching for this, and E epsilon and N epsilon, such that this converges to minus Laplace U and V. This converges to grad U, grad V, and this converges to U times V. So, and we found that it's interesting that you can really prove this line, which you know already it's true, by going through non-local equalities. Because this, as I said a couple of times, this equation here is just a Fubini result. And then showing existence is somehow being good with Taylor. And there's the only obstacle to show that this integral over the complement collapses to an integral of the boundary. And I'm putting this up here because tomorrow, when we discuss trace and extension theorems, something like this will become even more important. There's actually also some comments about the fractional mean curvature in this paper and its relation to the setting up, to the setup of a non-local divergence. So if you're interested in one possible viewpoint, how one can define a non-local divergence, you might want to check this out. But there's many ways how to define non-local divergences. So of course we don't claim anything special. So let me finish by somehow spoiling a little bit what will come tomorrow. So now we have the space V nu, which is somehow an analog of H1. Okay. Now we know this guy corresponds by trace and extension to H1/2. Now the question is, to which space does this guy correspond? It must be a space on the complement. So we look for spaces on the complement such that we have traces and extensions. Because once we have them, we can solve PDE, because we can then formulate or prescribe data in the complement, use the extension, and then use basic function analysis, which we do tomorrow. And our interest in Bielefeld, so to say, for many years has been robustness. So let's go away from the general nu to a very special one, to the fractional Laplacian. I said it, then we put an S here. You can put S, 2, let's just have an S. So then this will be TS. Now, in this picture, you know that this space converges, for a given function, but you have also gamma convergence to that space. Now, if you find such a relation, then it would be, of course, a dream if you would find a sequence of spaces that also converges to this. Yeah? And that's possible. And this is rather recent, from the last months or maybe the last 1 year, that we were able to do this. If you want to prepare a little bit for tomorrow, you don't have to do that. So you could go to a paper on arXiv by Florian and Torben. It's not the one about the maximum principle. So just, they have, I guess, 2 papers on arXiv, so it's the other one. And you can also go to a paper by Florian and myself, where we use the Whitney type covering argument that allows us to treat general domains and general nonlinear problems. You also find it on arXiv. So you don't have to go there, but if you want to somehow prepare a little bit, you could. So the plan for tomorrow is to study this diagram in detail. I Then we'll spend the third lecture on inhomogeneous Neumann problems and non-local to local limits. And then lecture 4 will be on, I will comment on parabolic Harnack and recent developments in parabolic Harnack. I think there's a shift in the program for Friday. Was it announced already?
So I am checking this now, but it will go on.
Okay, so it's just that we switch two lectures on Friday, so in total nothing will change. Thank you very much for your attention.
So, any questions? We've already solved the problems. All right, we've got to thank the speaker again and have a little coffee break.
So before you go, I have a couple of announcements. Today we have the social lunch. So I think you don't need to collect the money in advance, but we have to pay. So you need to pay when we arrive to the restaurant, probably at the end. I don't know if we will go one by one or I will need to collect. I will try that we go back one by one so you can get your receipt and everything is in
How much
time.
is it?
18.
18. Do they accept cards?
I hope so. You should. And also we should take the picture today. So if the weather is good, we will try to do it in front of. I think I will let you know, but at 2, please don't go fast. We will meet all together, we will take the picture, and then we will go all together to the restaurant. The lunch is at